Welcome to AI Paper Podcasts. Today we are looking at the paper Aletheia Tackles FirstProof Autonomously by Tony Feng Luong, and a massive team of researchers at Google DeepMind. Here are the key insights you need to know. Aletheia, an AI math research agent powered by the Gemini 3 DeepThink model, has autonomously solved 6 out of 10 research-level math problems in the inaugural FirstProof challenge. Operating with zero human-in-the-loop intervention during generation, the agent produced proofs that a majority of expert mathematicians rated as publishable after minor revisions. The model didn't just solve standard equations, it tackled highly abstract fields like symplectic geometry, equivariant stable homotopy theory, and tensor decomposition. Most impressively, for problem 10, the AI autonomously discovered an algorithmic complexity bound for a preconditioned conjugate gradient solver that beat the human author's official solution. This represents a massive leap in autonomous AI capabilities for research-level mathematics. Now that you have the high-level summary, let's unpack exactly how this agent pulled this off.
Yeah, and to frame why this matters specifically to you as an AI researcher or ML engineer listening to this, we have to look at the bigger picture. This isn't just a novelty of an AI doing, textbook math.
Right. It's
a masterclass in system design, inference scaling, and really the reliable autonomous generation of novel algorithms. We're talking about agents synthesizing completely new computational architectures that human experts actively missed.
Which is wild. And I want to start with that word autonomous because it gets thrown around a lot in our field, usually with a giant asterisk attached.
Oh, absolutely.
So clarify what the DeepMind team actually meant when they set up this FirstProof challenge, because these 10 questions, they released them in February 2026, and they weren't exactly leak code problems, right?
No, not at all. They were actual open problems, and lemmas pulled directly from the daily work of professional mathematicians. They were designed to be a highly rigorous, real-world benchmark.
Yeah.
And regarding the autonomy...
Yeah, how strict was it?
Incredibly strict. So in human academia, peer review is interactive, right? You submit a proof, a reviewer finds a weak spot, you revise it. The FirstProof authors originally suggested that this kind of interactive prompting might be an acceptable benchmark for AI.
As long as a human didn't inject new math ideas, I assume?
Exactly. But the DeepMind team completely rejected that leeway. They insisted on absolute zero human intervention during the generation phase. No hints, no nudges.
So how did they actually run it?
They set up 2 distinct agents, Aletheia A, which was powered by the February 2026 Gemini 3 DeepThink model, and Aletheia B, running on an older January 2026 base model. They literally just pointed these agents at the problems and required a best of 2 preferred solution for each one.
I did notice the only time humans touched the output was at the very end, using what the paper calls a verification and extraction prompt.
Right.
They basically just fed the raw text from Aletheia into a standardized prompt just to format it into latex.
Yep, just formatting. That guarantees the AI's mathematical intuition is completely uncontaminated by human hints. But, what's equally fascinating are the problems the agent didn't solve.
Yes, I am actually really curious about that.
It's one of the biggest takeaways for ML engineering here. It's the self-filtering. On 4 of the problems, specifically problems 1, 3, 4, and 6, the agents didn't just hallucinate some coherent-sounding but mathematically broken proof.
Which is what we're all used to seeing LLMs do.
Exactly. Instead, they returned a simple, no solution found.
That's incredibly rare. Usually, language models are, pathological people pleasers. They will confidently invent a theorem just to give you an answer. Why is this self-filtering such a massive win for scaling?
Because trading raw capability for high reliability is the primary bottleneck for deploying AI in actual scientific research today. If you're a working mathematician, you do not have the bandwidth to spend 4 hours debugging a confident hallucination.
Yeah, that makes sense.
A system that possesses the calibrated uncertainty to know when has exhausted its search tree and failed is vastly more valuable than a system that just guesses. It means you can actually trust the pipeline.
And that strict autonomy naturally brings up the question of cost. I mean, you can't just let an AI run a tree search forever without hitting massive compute limits.
You really can't.
The paper uses inference cost almost as a proxy for how hard these problems are, comparing the compute used here to their previous benchmark, the Erdu's 151 problem.
Right, and every single FirstProof problem required more compute than Erdu's.
And then you look at problem 7 and the chart just completely explodes.
Oh, it went vertical.
Yeah.
The compute cost for problem 7 was an order of magnitude higher than anything they'd previously observed. The architecture relied on a generator subagent, and a verifier subagent.
Okay.
For problem 7, the generator required vast amounts of compute just to formulate a single valid candidate step, which then required intense, prolonged back-and-forth interaction with the verifier to refine.
Why was that specific problem so resource-intensive? Was it mathematically computationally heavy or just conceptually elusive?
Very conceptually elusive. Problem 7 wasn't a random lemma. It was famously listed as an open problem in Shmuel Weinberger's 2023 book.
Prior to this challenge, humans hadn't solved it.
Never officially resolved, no. The search space for the proof was astronomically large. It forced the model to evaluate and discard thousands of dead-end logical branches.
Let's bridge the gap here between the theoretical math and the ML architecture, because the pure math in this paper gets dense fast. Take problem 2.
The local Langlands and Rankin-Selberg integrals.
Exactly. Both Aletheia A and B crushed this one, but the techniques they use, Gelfand-Kasdan restriction theory, finite Fourier analysis, level lowering on mirabolic congruent subgroups.
It's a lot of jargon.
For those of us writing neural networks instead of theoretical math papers, what's the intuition behind what the AI actually did there?
It is heavy jargon, but the mechanics are highly analogous to ML concepts. Think of a complex mathematical space, like a massive high-dimensional data set.
Okay, cracking with you.
What the AI did with Gelfand-Kasdan restriction theory was essentially find a rigorous way to project that complex space down to a finite, manageable subspace.
Like a dimensionality reduction.
Basically, yes. Once it restricted the problem to that smaller space, it applied finite Fourier analysis, which is conceptually similar to how we might use a discrete Fourier transform to find invariant features in pooled data. It executed this pipeline perfectly to derive a strict mathematical contradiction. 3 independent experts reviewed it and said the logic was absolutely flawless.
That's a great analogy. It's essentially feature extraction for abstract algebra. Now, contrast that flawless execution with problem 5, which deals with equivariant stable homotopy theory.
Right, involving incomplete transfer systems and slice filtration.
Aletheia A got it right, but Aletheia B failed completely. And the explanation for why it failed feels like a huge cautionary tale for anyone training large models on academic literature.
It's a textbook case of semantic brittleness. Aletheia B failed because it interpreted the term slice filtration in an archaic way rather than its modern mathematical usage.
But wait, isn't that just a retrieval issue? Like, if the developers had connected the model to a vector database of 2026 math papers using RAG, wouldn't it just pull the modern definition and solve it?
You'd think so, but it's much deeper than simple retrieval. Precise semantic definitions shift over time in advanced sciences. If a base model's pre-training data heavily weights historical texts simply because there are more of them.
Oh, because they've been cited for decades.
Exactly. More citations, more textbook references. The model's internal representations strongly associate slice filtration with that older definition. Even with updated context in the prompt, the model struggles to overwrite that heavily reinforced prior.
So it basically ignored the modern context because its weights were too deeply entrenched in the past.
Yeah. Aletheia B actually constructed a logically sound proof, but it was answering the completely wrong problem. It perfectly highlights how vulnerable LLMs are to the evolving semantics of literature.
Which brings us back to that astronomically expensive open problem we discussed earlier. Problem 7. Topology and Lie groups.
Yes.
The question asked if a uniform lattice containing 2 torsion could be the fundamental group of a compact manifold whose universal cover is rationally acyclic.
Try saying that 3 times fast.
Right. But Aletheia B actually succeeded here, which is wild considering the compute.
It's a landmark achievement. It pulled together incredibly heavy mathematical machinery. It constructed a strictly equivariant classifying map, utilized Bread and equivariant obstruction theory, and applied adiaboral localization.
Okay, pause right there. Break down how those tools actually achieve the result. Because it sounds like the model is just throwing a dictionary of topology at the wall.
It does sound like that, but it's actually a highly structured, elegant proof by contradiction. The AI used those tools to establish a parity constraint on a specific mapping property called its degree.
Parity, like odd or even.
Exactly. First, it mathematically proved that this mapping degree must be an even number. Then it brought in Kasparov's strong Novikov conjecture to prove from a completely different angle that the exact same degree must be exactly plus or minus 1.
Oh, I see. Since the integer 1 or negative 1 cannot possibly be an even number, the entire premise collapses.
Precisely. It built two massive conceptual bridges just to prove they couldn't possibly meet in the middle. It's a beautiful piece of reasoning.
But the contrast is stark here too, because while Aletheia B succeeded, Aletheia A completely bombed this exact same problem. The paper cites a critical flaw.
Yes, Aletheia A hallucinated that the rational Euler characteristic is multiplicative without establishing the proper finiteness assumptions. It just assumed a foundational rule applied where it didn't.
Why do models at this advanced level of reasoning still step on these basic mathematical landmines so confidently?
Because language models, fundamentally, are still statistical engines optimizing for coherence.
Wow.
If the model has seen the Euler characteristic treated as multiplicative in thousands of other contexts where finiteness was implicitly assumed, it might statistically infer that the property is universal.
So it just drops the edge case constraint.
Exactly. This is why the verifier subagent is so critical, though in Aletheia A's case, the verifier failed to catch the dropped assumption.
That tension between being statistically coherent and rigorously correct perfectly segues into the most controversial result in the FirstProof challenge, problem 8.
Symplectic geometry.
Right. Asking if a polyhedral Lagrangian surface in 4D space, where exactly 4 faces meet at every vertex, necessarily has a Lagrangian smoothing.
And this is where the highly subjective nature of human peer review really rears its head. 5 out of the 7 evaluating experts rated the AI's proof as correct. The model used techniques called exact local smoothing and Lagrangian suspension.
For those of us dealing in code, what makes a Lagrangian smoothing so hard to map out? What is the AI actually trying to do geometrically?
Imagine you have a 3D model in a video game that's very low poly. It has sharp, rigid vertices where flat faces meet. Smoothing it means modifying those sharp corners into continuous differentiable curves without breaking the underlying geometric rules of the space.
Okay.
In a 4D symplectic space, the constraints for what is allowed to be smooth are incredibly rigid. The AI correctly demonstrated how the tangent cone at these sharp vertices factors into an orthogonal product. It handled the local geometry perfectly.
So if the geometry was right, why were the human experts torn?
Because of the communication standard required for something to be publishable with minor revisions. The contention was in step 3 of the proof.
What happened in step 3?
Well, after smoothing the local vertices, the AI had to interpolate those perturbations along the connecting edges. Several experts felt the AI's explanation for this interpolation was sketchy. Yeah, it lacked the necessary rigorous, step-by-step detail to be accepted into a journal as is. The experts agreed the underlying geometric intuition wasn't wrong, but the AI essentially hand-waved a step that human reviewers demand be spelled out.
It's the classic show your work problem from high school calculus, just scaled up to 4D geometry.
Perfectly said. It illustrates the gap between arriving at the correct truth and communicating it to human institutional standards.
Before we get to the final problem, I want to give some dedicated time to problem 9, because it involves algebraic relations of tensors, which sits right on the boundary of pure math and machine learning.
Oh, definitely. And the researchers ran an extended generation variant for this one called Aletheia F.
Right. And Aletheia F successfully utilized multilinear matrix flattenings to bound ranks and map valid configuration graphs.
Yes.
If you've ever dealt with torch.reshape or inops in PyTorch to flatten a multidimensional tensor into a 2D matrix just so you can compute its rank or pass it through a linear layer, this sounds highly related. What was the AI achieving algebraically?
It is highly related. In pure math, analyzing the properties of a high-dimensional tensor directly is incredibly difficult. What Aletheia F did was abstractly flatten these tensors along different dimensions to analyze their matrix representations.
So it's looking at slices of it.
Exactly. By doing this multilinear flattening, it could rigorously establish bounds on the tensor's rank. It then used those bounds to map out a graph of valid configurations, essentially proving which algebraic relations were actually possible.
It's a fantastic example of the AI using a structural transformation to make an intractable problem solvable.
Absolutely.
Now, I have been looking forward to this next part, because problem 10 is where this paper stops being purely about theoretical mathematics and starts directly impacting how we build ML systems.
Yes, this is pure algorithmic optimization territory. If you work with large-scale linear solvers, big data, or tensor operations, problem 10 is the core payload of this deep dive into the source material.
The setup was a task to compute a canonical polyadic or CP decomposition of unaligned tensors with missing entries. The twist is that some of the modes are infinite dimensional and constrained to be in a reproducing kernel Hilbert space, or RKHS, and they needed to solve the mode subproblem using an alternating optimization approach.
To really appreciate what the AI accomplished here, we have to look at the computational complexity constraints.
Lay out the variables.
Okay, we have a variable n, which is the product of all tensor dimensions. It's astronomically large. We have q, the number of observed entries, which in real-world datasets is usually in the millions.
Okay.
And we have n and r, the mode size and the rank, which are relatively small. The objective is to solve a dense linear system of size nr by nr.
But you can't just form the matrix.
No, you cannot ever explicitly form that matrix, because doing so would cause O of n cubed r cubed in compute. And you must completely avoid any operations that scale with the astronomical n.
Now, the human authors who wrote this first proof problem had an official solution. They used a solver that ran at O of QNR per iteration. Since Q is the massive number of observations, having Q inside the iteration loop is a huge glaring bottleneck. It means every single step of the solver scales with your massive data set.
It's terribly inefficient.
But Aletheia A autonomously discovered a vastly superior method. It derived an optimal block-Jacobi preconditioner that runs at O of n squared r plus nr squared per iteration. It entirely stripped the massive Q dependency out of the preconditioned conjugate gradient, or PCG, iteration loop.
Which is incredible.
How exactly did it bypass the need to loop over the data?
It achieved this through a strategy we can refer to as pre-aggregated geometry. The AI mathematically realized that instead of processing the spatial observations during the iteration, it could aggregate the unaligned data geometry up front.
Before the loop even starts.
Exactly. During the setup phase, before the iterative Krylov loop begins, it computed n-independent symmetric R by R matrices, denoted as E super I.
So it's the difference between doing a heavy computation once during the initialization phase versus doing it inside the forward pass loop for every single batch.
That's exactly it. By doing this heavy lifting before the loop, the actual matrix vector product inside the PCG loop evaluates strictly independent of Q. It shifted the computational burden entirely out of the iterative bottleneck.
That's so smart. And we actually have a perfect external baseline to compare this against.
We do.
An independent team, Aryan Mokhtari and David Woodruff, did a public run of the Gemini 3 DeepThink model on this exact same problem. The paper refers to their result as Approach 2.
Yes.
Comparing Approach 1 from Aletheia's autonomous run to Approach 2 from the public run is fascinating, because Approach 2 completely bypassed the pre-aggregation idea.
Instead, it kept all Q spatial observation vectors in memory, meaning it still had to loop over all Q points to accumulate gradients on the fly at every single iteration.
But it did have a trick, didn't it?
It utilized a brilliant algebraic trick for its Krylov tracking. Standard PCG requires an inversion of the kernel matrix, which is an O of n cubed operation. That's not just slow, it's numerically disastrous for nearly singular kernels.
Yeah, inversions are a nightmare.
Exactly. Approach 2 managed to analytically track pseudo-residuals, which completely canceled out the inverse kernel operation in what they call inverse-free tracking.
Which, mathematically speaking, is incredibly elegant. It avoids the inversion completely.
It is beautifully elegant for memory constraints, but it misses the forest for the trees computationally.
How so?
While Approach 2's inverse-free tracking is clever, its iteration cost remains bounded by O of n squared r plus QR.
Oh, the Q is still in there.
The Q is still in there. Because Q is usually millions of observations, forcing the loop to process Q items, every step creates that massive bottleneck.
It essentially optimized the math, but failed to optimize the system's architecture.
Exactly. Aletheia's autonomous choice to use pre-aggregated geometry with a row-wise block-Jacobi preconditioner proved to be the vastly superior computational architecture for large-scale, real-world datasets. It optimized for the system, beating the human baseline complexity bounds entirely on its own.
The implications of this are staggering when you zoom out. We are really looking at a paradigm shift here. We have an autonomous agent synthesizing multidisciplinary research mathematics, navigating everything from Langland's programs to topology, and successfully inventing optimal algorithmic architectures that outperform human-designed linear algebra solvers.
And that reality leads to a profound question for the future of our field.
Let's hear it.
Aletheia just autonomously derived a novel preconditioner and a pre-aggregation strategy to optimize an iterative linear solver for tensor decompositions.
Right.
If these AI agents are already capable of inventing more computationally efficient matrix vector methods, what happens when ML engineers turn these exact same agents inward? What happens when we task an agent like Aletheia to optimize the underlying mathematics of its own attention mechanisms, or to derive mathematically faster architectures for neural network training? We could be looking at a near future where the next major breakthrough in AI training efficiency is mathematically proven and algorithmically optimized by the AI itself.
That is a phenomenal thought to end on. Thank you for joining us for this deep dive into the source material. We'll see you next time.